Welcome back from the break, guys. If you've just joined us, we are doing your final exam prep to help you with the upcoming exams. If you're constantly running out of data, then this next competition is just for you. Wazo Matrix is bringing you the hashtag WazoWinner competition, where 2 lucky matriculants stand a chance to win 2 gigs of data. All you need to do to enter is head on over to our Facebook page and all of the details will be there. Thank you so much, Nicola, and over to you.
Thanks so much, Luni. All right, let's get going with some trig, as I said, one of my favorites. Okay, so we're going to start with question 2, and it's a proving an identity question, which is something that a lot of people struggle with. Okay, let's read it. It says, prove the following identity. So we need to prove that cos squared x minus cos x minus sine squared x all over 2 sine x cos x plus sine x. We need to prove that that is equal to 1 over tan x minus 1 over sine x. Okay, always with proving identities, really one of the most important things to remember is that you cannot assume that the left-hand side is equal to the right-hand side in order to prove that the left-hand side is equal to the right-hand side. So you really need to remember to break it up. Okay, so we have a left-hand side over here, and we have a right-hand side over here. And what we need to do is we need to work with the left-hand side, and we need to try and use our identities and various definitions to turn the left-hand side into the right-hand side. Okay, so let's start with that. I'm going to start with the left-hand side. Okay, so we know that when we do trig identities, we're going to be using a lot of very common skills and tools. We might be using factorizing, we might be using multiplying out, those sort of things. We might have to add and subtract fractions. So let's see what tools we need to use here. In the numerator, we have cos squared x minus cos x minus sine squared x. All right, so just be careful here. You don't have cos squared x plus sine squared x, so you can't use that identity. But hopefully you know from your double angle formulas that cos squared x minus sine squared x is equal to cos of 2x. All right, that's not going to be very useful though, because if I change that into cos of 2x, the numerator is going to become cos of 2x minus cos of x. And the reason that's not useful is because I can't really work with ratios when they have different angles. So let's try and bring that cos of 2x back into a cos of x by rewriting the cos of 2x as 2 cos squared x minus 1. All right, and that's going to be a lot more helpful, because then what we're going to have is an expression in the numerator that we're actually going to be able to factorize, and we're going to see how it all comes together from that. Okay, so we're going to write, I shouldn't have erased that, so the left-hand side, this and this is now going to become 2 cos squared x minus 1, and then of course don't forget the minus cos x over there. Okay, let's turn our attention to that denominator. In the denominator, we could possibly turn that into a sine of 2x, but again, that's not going to be useful, because then I'm going to have a 2x and an x, they're different angles, all in the same denominator, and I can't work with different angles like that. So rather, I'm going to try the approach of factorizing. I'm going to factorize a sine x out of there, and I'm going to be left with 2 cos x plus 1. All right. If I look at that numerator now, I now have a quadratic expression, a quadratic trigonometric expression. And I can factorize that into 2 cos x plus 1 and cos x minus 1. And that's all over sine of x times 2 cos x plus 1. Okay, so remember, all I did to go from there to there was factorize that quadratic expression. Okay, and very beautifully now, I can cancel that factor with that factor over there, and that leaves me just going to come onto this side over here. Just going to erase that. So very, very beautifully, once those have cancelled, I'm going to have cos x in the numerator, cos x minus 1, and of course I have my sine x in the denominator. I can break that numerator up and put each part over the sine x. So I've got cos x over sine x minus 1 over sine x. And the last thing I need to do is convert this into a 1 over tan x. Remember that tan x is equal to sine x over cos x. So therefore, 1 over tan x is it's the reciprocal of that. It's going to be cos over sine. So this can now be simplified to 1 over tan x, and then of course I've got my minus 1 over sine x over there. All right, and therefore I've now proved that the left-hand side is equal to the right-hand side. Okay, let's move on to a general solution equation. You will always get a general solution trig equation in any paper too, so it's really important that you focus and understand what we do here. Okay, so I've got 4 plus 7 cos theta plus cos of 2 theta is equal to 0. Now, as I mentioned in the last question when we were doing the identity, I can't work with different angles over there. So I'm going to have to take this double angle and I'm going to have to convert the cos of 2 theta into a more usable ratio. So always with cos of 2 theta, you've got your 3 options, the 3 different formulas that you'll have on your formula sheet. I'm going to again use the fact that cos of 2 theta is equal to 2 cos squared theta minus 1. And the reason I'm using this particular equation is that I'm going to have cos of theta, and that's going to leave me with an equation in only cos of theta. So this is going to become 4 plus 7 cos theta plus, and this I'm now going to write as 2 cos squared theta minus 1, and that's all equal to 0. Okay, let me just simplify. The 4 minus 1 gives me 3, so we can see that I now have a quadratic equation. So 2 cos squared theta plus 7 cos theta, and I have plus 3, and that's all equal to 0. I can now factorize this expression. I'm just going to use my little cross on the side here. That's what I like to do. Maybe I'll just do it up here. So I've got a 2 and a 1, and the factors of 3, I've got a 3 and a 1 over there, and they're both positive. So I can see that my factors are 2 cos theta plus 1, and my other factor is cos of theta plus 3, and that's equal to 0. So now I've got the product of 2 factors being equal to 0, which means that one of those factors must be equal to 0. So therefore, cos of theta must be equal to -1/2, or cos of theta must be equal to -3. So let's just look at that solution. Okay, so we know that cos of theta never goes above 1 or below -1. So if we just remember what the function looks like that. So it starts at 1 and it goes down to -1. So there's no value of theta that is going to make cos of theta equal to -3. So there's no solution from this particular equation. So this is no solution. No value of theta is going to make cos of theta equal to -3 because it never goes below -1. So I need to focus all my attention onto this part of the general solution, and I'm going to do that on the next page. So I know that cos of theta is equal to -1/2. So I'm going to get my reference angle first. My reference angle is the inverse cos of 1/2. For your reference angle, you're always going to use a positive number over here. And that, well, hopefully you know, it's a special angle, is equal to 60 degrees. Now I have to decide which quadrants I'm in to get my values of theta. So I'm going to use my cast diagram, and I can see that cos, so I want the 2 quadrants where cos is negative. And cos is negative in quadrant 2, and quadrant 3. So those are the two quadrants that I'm going to have my solutions. So in quadrant 2, I'm going to say that theta is equal to, now in quadrant 2, I've got 180 minus theta. So it's going to be 180 minus 60 degrees, and that's plus K360 always, with sine and cos, it's your K360. So therefore, theta is equal to 120 degrees plus K360. And the final part of my solution is going to be my quadrant 3 solution. So in quadrant 3, I'm always 180 plus theta in quadrant 3. So therefore, my solution is going to be equal to 180 plus 60 degrees plus K360. And that is equal to 240 degrees plus K360. Okay, so you were asked for the general solution for that question, so you don't have to substitute any integers into K to find the more specific solutions. You can keep it in that form as the general solution, and you can see you have an infinite number of solutions. Okay, so that's it for this segment of the trig. In the final segment, we're going to be doing a bit of Euclidean geometry. So back to you, Luni.
Thank you so much. Guys, we are going to take a quick break, but before we do, don't forget to send us your questions, your comments. Let us know how the exam prep is going so that we can assist you as best as we can. We do have that competition as well, so please enter so that you can stand yourself a chance to win data. Don't go anywhere, Matrix. We'll see you straight after this.